Hello and welcome to the viscoelasticity of gummy worms. Before going any further, we should probably talk about polymers, seeing as gummy worms are polymers. Polymers are made up of hydrocarbon chains, which are primarily hydrogen and carbon atoms. These chains consist of many smaller units, which can include other various elements. Polymers can be found both in nature and can be man-made. They also come in various microstructures, which result in varying degrees of strength. To help give you a better idea, imagine these guys, which make up these guys, which all make up this guy.
Similar to metals, polymers deform under strain and as a function of time. Creep in polymers doesn't follow the same graph. In fact, it goes up over time until a point where the load is taken off, and then the strain starts to dissipate, but it still is present even after the load is taken off. Of course, since polymers cover so many different types of materials, it depends on which polymer is used on how this will go. For truly elastic material, as the load is applied, the strain increases rapidly or almost instantaneously, then holds constant until the load is taken off. Then once the load is removed, the strain instantaneously goes back to zero. For this type of material, strain builds up in the material until the load is removed, but then it holds the strain even after the load has been removed. So if we were to merge the two, it looks closer to this graph. As the load is placed onto the polymer, it increases in strain, but not instantaneously. Then, after it gets to the peak, you can see the load is removed, but the strain slowly comes back, but it still leaves some kind of deformation and residual strain in the material.
The gelatin and the gummy worms used in this experiment are the main ingredient that gives the worms the type of viscoelastic behavior that allows us to use it for creep analysis. In the experiment we performed, the gummy worm was attached to a surface at the top and had a weight hanging from the bottom. It took multiple tries, but we eventually found a setup that worked well. Once the weight of 138.26 grams was released, the initial deformation occurred and it was approximately 1.5 inches. From there, it took a long time to deform the final inch before the weight broke the gummy worm.
To conclude, we were able to successfully demonstrate the gummy worm's viscoelastic nature. This attribute makes them susceptible to a unique form of torture. This does not affect their taste, however, as they are still delicious.